heard somebody say recently, they said they think RAG is dead. In particular, they pointed to some of the newer models that have these like giant context windows. When you hear this, like somebody says, context windows are so big, or some of the intricacies of how something like retrieval augmented generation works at scale, therefore we need a new technology. What's your response to that?
Yeah, so my response might slightly surprise you because I somewhat agree with that observation.
Hello, I'm Ben Kus, CTO of Box. Today we'll be talking about technologies that power AI, and in particular, retrieving data using vector embeddings. Today joining me is Bob van Luijt from Weaviate, who has been involved in vector embeddings from the early days. Bob, welcome. So on our explainer series for AI, we have talked about RAG, secure RAG, and other search technologies. And today we're going to do a deeper dive into some of those technologies with Bob here. Bob, can you give us an intro about yourself?
Yeah, so first of all, Ben, thanks for having me. This is great. So it's like, I love the series. So I'm involved with this stuff and stuff being these models and these embeddings. This is my 12th year right now. And so I go way back to the beginning. And I've started working on Weaviate 6-7-ish years ago, where we thought like, hey, wait a second, can't we use these embeddings for better search and retrieval? Well, that's how everything started. For the listeners, back then, that was like a tiny niche. I remember the very first ever meetup I organized in New York where exactly 0 people showed up. So tiny was the niche.
Yeah.
So it's like, that's how far back I go. But one of the things, of course, that happened was that in AI or machine learning, and we're probably going to talk about that more, these embeddings play like a, prominent role. And all of a sudden there was like a new data type in the world that people started to use a lot. And that's kind of, what I've seen like literally the beginning of until today where they're omnipresent.
Yeah. I sort of believe that embeddings are almost the unsung hero of some of the AI revolution, including like in the enterprise. But before we get too far, for people who don't spend all the day and night with it, can you describe or to define the terms embeddings, vectors, vector databases? Can you give an overview on sort of what these mean and then sort of why they power AI technologies?
Yeah, so the easiest way to think about embeddings is as coordinates. So how you would place them on a map. And what people try to achieve, especially back in the day from an academic perspective, was like, it started mostly with language, not exclusively, but mostly with language, where people started to say like, can we somehow say something about how words relate to each other? And the way they did that was like by placing them on a map. For example, if you would say like words like Eiffel, and then the words tower, they're closely together, and you have Eiffel and tower, and you have Paris. But maybe you might find a word like, I don't know, Delaware, that would be somewhere completely different on that map, but there would be other things related to that word. And I'm more than happy to dive into like how they did that, how they cracked the nut, but that sits at the root of it. And if we think about images or multimodality, you do the exact same thing as you do with words, but now with single individual pixels. So the thing is, how can we predict something about how words, how pixels, how audio relates to each other? And that sits at the root of what the embedding is. And what the database does, it's almost like in what's in the name, right? The database stores that stuff and you retrieve that stuff. So that's what it does. And that's what the embeddings do. And they're so well suited for machine learning and AI.
Okay. So if I'm thinking about this, so coordinates on a map would be like a couple different, like kind of like longitude, latitude. So tell us about like exactly like what in embedding, if somebody wants to visualize it, what would it be if they just actually looked at it?
It looks like coordinates you would get like on a map, but instead of like 2 or 3, you have like hundreds and sometimes thousands. So you see often like 1537 is like the size of embeddings that are used a lot. And sometimes people ask me, they're like, Bob, why so many? What's the difference? And the way to think about it is this. Let's say that I would give you a map to a supermarket and I would say, like, just find me some, some chips or something, right? So if I give you 2 dimensions, you know where to go in the store, but you also have to look up and down to actually find like, the bag of chips. But if I would give you a 3rd dimension, I give you more information. So now you not only know where to go on the X and Y coordinates, but you also know where to look in the shelves. We do the same thing, but then just in like a hyperdimensional space. So that's where we keep context. So the smaller, the lesser amount of embeddings, the lesser amount of information we have. And it's always a little bit a play like, so how many dimensions do you need in your embeddings to actually keep context?
Yeah.
That's like for the scientists to figure out.
Yeah.
But that's what it does.
So one of the like historical technologies that search would use in especially in enterprise sense is this idea of like just find the words, right? And so then into your example of the coordinates, like one of the common different examples people would use to highlight why this is a challenge is if I said, hey, I want you, I have a question about what programming language is used for this topic. Versus a question that was like, what did you have for breakfast this morning? The word Java might appear in the answers in both places, but that's a very different sort of embedding space. Talk about how the embeddings would handle the difference between the same word, but in very different contexts.
The words that we have in the embeddings, they have a certain meaning attached to them, right? So, for example, you mentioned Java. So we have the Java programming language and the cup of coffee, coming from Java. But there are also certain words that have no meaning. So then if we use them and we embed them in that vector space, they're not that valuable. We're going to talk about that, I think, in a little bit.
Yeah.
But where it gets the most value right now is that if I'm trying to retrieve a document from something or a data object for something where I don't know the exact matches. So let me give you a super simple example to stick with my example of the Eiffel Tower. If I have a document that states the Eiffel Tower is in Paris, then in the traditional sense, the only way to retrieve the document was by searching for Eiffel or Tower or Paris. But now I can retrieve that document thanks to the embeddings by searching for landmarks in France. And that's the power of these embeddings.
And it is a traditional challenge for all enterprise search systems where if somebody said, what are places to go in France that are interesting, then it would never retrieve that document because it never said those words in there. So this is a very powerful technology. Okay, so tell us now, if that's embeddings and that's the vector representation, what is a vector database then?
So when we deal with any data type, right? So that can be a document, can be a graph connection, can be time, can be anything. What you start to tend to see is that infrastructure emerges that is good at that specific data type. Right? So that is where the vector embedding came from. So, or you say like, oh, might be like a bolt-on to an existing solution, which is fine. It's great for certain use cases. But sometimes if you have use cases where you really depend on these semantic search features or similarity searches for images, audio, and those kind of things, you might want to have a specific data store for this. Now, on top of that, as somebody building such a company, I actually know that it's not only the architecture under the hood, but also the types of use cases that people have and how they build these kinds of applications, that you start to add a lot of functionality to the database that is specifically suited for those types of AI use cases. So it's a combination of the storage engine that is good at dealing with these embeddings and the data that it represents, but also the additional features that you add on top of that enables people to just make it easier for developers to build solutions. Or what we like to refer to as AI native solutions.
Yeah, a typical database, one who's been around for 20 plus years, like it's good at looking up things, looking them up quickly, right? And so why not just look up the vectors fast, right? The databases seem like they should be able to handle that. Can you talk a little bit about the challenge about why vector databases are a specific technology that has a series of technical challenges associated with it?
Yeah, that's a great question actually. So the analogy that I often use, or the comparison is with cars. So if we build a car where the car represents the database that we're building, we need to make some trade-off decisions in the architecture we choose, right? So if you say like, this car needs to be like super fast, that's the only thing we want. We want it to be like super fast. Then what you do is like you make trade-offs in aerodynamics, and it's low and it's like only fits two people and those kind of things. If you say, no, this car, we just need to, I need to use this car to bring I have a huge family. They need to be able to drop them off at school. Now, all of a sudden, you might be looking at a van or those kind of things, right? And doesn't have the same aerodynamics, but that's the same thing for databases. So what you start to do is that you start to optimize the databases for the types of workloads that they support. Let's not forget, and this is really important, this is not only limited to the underlying architecture, what these things are good at, but also what we refer to as the developer experience. So the way that you give access to the data and how people build on top of your database, the more narrow focus you have, the easier you can make it, the lesser of a hassle you can make it to build solutions on top of such a database. So it's really that trade-off, that core architecture if you have a narrow focus of use cases, in our case, that's AI native cases, you can basically take a lot of abstraction away, just make it super easy, like time to value, right? So you just start building and, a couple hours later, you're ready to go to production.
Yes. Okay, so let's talk for a minute. In this series, we've talked about not only the concept of RAG, or retrieval augmented generation, that typically can use vector databases and embeddings, but also the concept of secure RAG, or the ability to also process permissions. Because the naive way to do it, of course, would be to put all of your data in enterprise into a vector database and do a query and find the data. But of course, most people don't have access to all the data. In fact, probably no one in any organization has access to all the data, or no two people have access to the same thing. So then there's this idea of you have to kind of filter the data in some form, like what do people have access to? What do they own? What groups are they in? What folders do they have access to, and so on. So can you talk about how that, in relation to your technology, is either completely part of the optimization, or it's a challenge for you? When you're adding these filters on top, or even complex filters on top of the database, what does that do to your database technology?
Yeah. So first of all, it's super important, right? Because in the pre-AI world, everything that we were doing was very a binary, if you will, right? So it's like so for example, you could set a filter in your database, and it could say like, only show this document if it's this person looking at the document. If you want to go deeper, you could like have RBAC and those kind of things. But with AI, that changed a little bit, right? So we went from binary to more like a floating point orientation, right? So where we were predicting stuff. So the problem with predicting stuff is that if you have data that's like where we need to guarantee that some people have access and other people do not have access, we can't just throw it into the context window and then prompt it saying like, please don't show this to Ben, only show it to Bob, and vice versa. I don't think, that a lot of people from the security departments are going to, accept that, right? So like, we prompted it correctly. So what you start to see, and this is again a beautiful thing of the vector database, is that we start to use these traditional mechanisms like RBAC inside the context window when we're doing RAG. So when a user has a query, we're using a traditional RBAC mechanism to do vector search, or hybrid search, or those kind of things. That goes into the prompt, and therefore we can guarantee that the results are secure, because we can guarantee who has access and who has not, while we still have all the fancy new capabilities that AI offers us.
Yeah. We've said on the show before that AI doesn't keep secrets. And so, you should never expose your AI to something for that query for that person that they don't have access to. One of the challenges that comes up is not only doing the technology, but doing it at scale. So like at some point you have a database, you get something working, but then like at Box, we know that like the more that you add more vectors, the more that you try to do this across an awful lot of data, especially enterprise scale, you start to run into different challenges. Can you talk about a little bit about why this is not as simple as just getting any old vector database and throwing everything in there? Like what are the types of scale challenges, and where do they come from?
Great question. So back in the day when we started with all this stuff, right? So that we didn't have these scale challenges yet, right? Because use cases were small, people were experimenting. And when we saw that most of the data went into memory. So for the people listening who really want to dive in, the algorithms that are used under the hood are so-called approximate nearest neighbor algorithms, and they live somewhere. So they live in memory, they might live on disk, or they're like smart ways to just have them go between memory and disk, or disk, and even offload them into storage buckets like S3 and that kind of stuff, right? And what started to happen is that some of these algorithms were optimized for certain places in the stack, if you will. So what you started to see is that if people have use cases where speed is of the essence, or people say like, we cannot sacrifice any milliseconds because it would hurt like user experience or those kind of things, you're bound to memory, right? Then it's just memory. But if people say, well, you know what, we have more like archival use cases and those kind of things, so we store them. And to be honest, we don't really care if you have to wait for these results. Then you might store them on disk or those kind of things. So what you started to see, and we often refer to them as like the multi-tenancy use cases, because they nicely go, hand in hand with multi-tenancy use cases. If you want speed, memory, very expensive. If you want to have those types of multi-tenancy use cases, you probably want to use disk. So let's take Box as an example. Box is ideal from a multi-tenancy perspective, right? So That's like the disk-based solution. So rather than saying like, let's throw every file ever stored at Box securely in memory, that's going to be expensive. That's a lot of memory. We don't do that, right? So we say like, okay, we want to store it more efficiently on disk. And then you have that security again, multi-tenancy wise, that you can guarantee that I can guarantee that if I don't give access to Ben, he can see my files and vice versa and those kind of things. So those are the types of architectures that start to emerge in vector databases. And so if we look at our customers, we see like memory use cases, disk-based use cases. Depends on what people are building.
I heard somebody say recently, they said they think RAG is dead. In particular, they pointed to some of the newer models that have these like giant context windows. When you hear this, like somebody says, context windows are so big, or some of the intricacies of how something like retrieval augmented generation works at scale, therefore we need a new technology. What's your response to that?
Yeah, so my response might slightly surprise you because I somewhat agree with that observation. I just don't agree with the conclusion. So because indeed the context windows are growing. There's like by the way, there's a great website from our friends over at Contextual AI, isragdeadyet.com, because indeed these context windows, they are getting bigger. But let me tie this back to your point about like secure rag and what the context window actually does, right? So let's say that I take a sentence, right? In a tiny sentence, so it's a tiny use of the context window, so Ben talks to Bob. So what it does, it basically says like, I take the words Ben talks to, etc., tokenizes them, but the token is a number which is basically a reference to a vector embedding. So a context window is just a big array of vector embeddings. So even if we want to make that very big, we at some point will be looking at a way to efficiently store these embeddings that are in the context window. What type of technology is really good at storing embeddings? A vector database. Plus, going back to what we discussed with secure rag, it's kind of nice that the database gives you these more traditional kind of ways to do RBAC and guarantee that certain tokens are not in that context window when you present it to the end user. So my conclusion, this is where I differ from the conclusion. Yes, the context windows are getting bigger. Yes, that's very powerful, but that does not mean that rag is dead. That means that like rag is like hyper alive because the vector database and the context window are just going to become the same thing, right? It's like you need a database for a big context window. So I agree with the observation, but I disagree with the conclusion because they're just got to be married together.
And to the point, like we just did an episode on context rot, which we can include in the comments. And so not only do you want to make sure that you fill up the context window with the appropriate info, but you want to make sure that you don't give it too much other extraneous data because it will confuse the models in many cases. Can you talk a little bit about multimodality and how vector databases work with that model?
Yeah, so just give some historical context. So for people who are interested in this, is that everything that's been happening, especially from an academic perspective and way back, was to get that question answers like, how do humans observe the world? And can we do that in an artificial way? And we've seen a lot of success with analyzing text and reading text. But the thing is, a human child doesn't start, observing the world by reading, right? Reading comes later. And we've seen like a lot of very highly intelligent people in the past who couldn't, read one letter, right? So we know that if we build these models, that doing it purely based on text might not really be representative for or getting closer to how humans do it. So how do humans do it? Well, we don't really know, or the academics working on this stuff don't really know, but what they do know is that observing the world plays a role in that. So if you look at the early multimodal models, it was not only text-based, image-based, and audio-based, but it even had like heat maps in it and those kind of things, right? So it was like, how much senses of the world can we compress into that algorithm? And the powerful thing that they do is that they basically make a relation, and I'll give an example in a bit, between, for example, these words, pixels, audio, and those kind of things. Well, how do you do that? Well, if we can say that, for example, the word apple has a relation to the phone or the products from Apple, but also the fruit, then if you have an image and a certain set of pixels where you see the fruit and the product, you can generate embeddings that are closely related to each other in the same vector space. And that's what a multimodal model does. So you say, okay, I'm going to give you something in this modality, text, image, audio, what have you, and give me the representing embeddings back. And actually, funny thing is, turns actually out that if you train multimodal models, that they actually perform better even in a single modality. Isn't that interesting?
That is very interesting. And I think like some people like naturally think that one of the first things the models do would be to convert it to text to then look it up. But when you have a multimodal embedding, you're actually directly translating the pixels on the screen into an embedding, which is kind of crazy to think about. Like the embeddings model basically understands the picture in different ways as opposed to understanding the description about the picture, which is kind of mind-blowing for many people, I think.
Really, if you think about it, like, let's say that we would have 1 pixel images, would be a little bit weird, but let's say for the sake of argument, right? Then we could say, well, if I have the word apple, right, or like a Granny Smith apple, and I just have a green pixel, they relate to each other, right? So if I would have a single pixel of a Granny Smith apple, it would be green, or type of green. So I can relate that in vector space to the same word of like, or the word sequence of Granny Smith apple. Often these things are not that complex if you know how they work under the I mean, not that complex to understand. To build is a different story, but
yeah,
to understand.
So let's talk for a minute about hybrid search. So there's
Yes.
so we talked in the world about vector embedding, search, the techniques involved to go through that, and there's this old traditional world of like just looking up keywords and so on. When somebody hears the word hybrid search, what does that mean, and what should they be thinking?
Unfortunately, I have to say that the vector search is not a silver bullet. So we were, of course, hoping for that, but that's not the case. So, and let me give you a very simple example. So just imagine that you just have like, you have like let's take Box as an example, right? So let's say I have like dozens and dozens of hundreds of thousands of invoices, right? So I have embeddings for these invoices. And if I would say, show me all the invoices with office supplies, it would do an amazing job at that because it knows like pens and, well, whatever stuff you use in office, right? So it would retrieve those info. It does a great job at it. But now you have the challenge that you have like a lot of invoices. And you're like, oh no, I'm actually looking for invoices, for example, with a specific ID or an order number or something.
Yeah.
Now, these order numbers, that is something that vector search is really bad at. So if you would say like an order number with ID 123 ABC, yes, it would place it in vector space, but because the data doesn't have a train on it, it can mean anything. So it's like, it's meaningless in vector space.
Is it like, so in essence, the embeddings algorithm doesn't actually try to assign meaning to, they almost like sort of would describe it in vector space as just a number or some sort of meaningless identifier. Is that the way to think of it?
Yes, or another way to think about it is like, I gave the example earlier of the word Eiffel, and then chances that you would see something, for example, Tower or Paris around it, that kind of makes sense. Or even Tokyo, because Tokyo is an Eiffel Tower. So you kind of, that makes sense. But let's say that we take a word like the word the. The is too ambiguous. There's just too many words around it. So it flows somewhere in the middle of that vector space. It's meaningless. Now, with those kinds of IDs, as I just gave, they're not incentive, but like might float around on the outskirts and they don't really mean anything. But they mean something to us because we know that these invoices of office supplies, that's the meaning. So what we do is that you use traditional forms, and the algorithm that's used the most there is BM25, which is for the technical audience, generates a sparse embedding. So what it basically does is just like, if ABC123 sits in that data set or in that invoice, if you will, I'm going to rank it very high. And then I'm going to look at also the fact that it has like office supplies in there. So if I have an ID 123 ABC, but maybe for food or those kind of things, I'm going to rank that lower. So that combination of vector search with what we call sparse search, or like more traditional forms of keyword search.
Yeah.
That is a super powerful combination. But nowadays we know there's one more powerful combination than hybrid search.
Which is?
Cliffhanger. Yeah. So that's what we refer to as agentic search. So So what agentic search does is that the agents in the database still use the power of hybrid search. But now let's say that I say, well, I'm looking for that invoice around office supplies that has these kind of ideas in it, but these invoices should be filed between this date and that date. Now what the agent does, the agent itself does the hybrid search, but it also understands looking at the invoices, hey, there are dates on the invoices. So now I'm going to set a traditional filter for the date fields. Back in the day, we had keyword search, we got vector search, we got hybrid search, and now we have the best of everything combined in agentic search.
Got it. Yes, and we did an episode on agentic search also, which we'll include in the comments. So putting it all together, you take these different technologies, layer them, and then have AI interpret them to give you the ability to find the information, sort of using all these different techniques. I'm personally a huge fan of agentic search, but agentic search that uses these techniques because that's how you get the best agentic search. It's like all the challenges that you mentioned, of course, we face at Box in terms of making sure that we help you find the right data, having the scale challenges, having the performance challenges, and so on. The great thing would be that for the first time ever, like an enterprise would be able to conceivably be able to find information like this. And historically, they've never really been able to do this. So I think it's incredibly exciting. As we close up here, tell us, when you're thinking about what's like now emerging or what's coming next, or sort of how you see this whole sort of underlying technology evolving, what are your thoughts on what to keep track of?
So something that I'm extremely excited about. So the agentic search, what we just mentioned, is something that we refer to as a query agent because it helps with querying. 2 years ago, somebody showed me something, but they said, hey, actually, if I have like a RAG pipeline and I use this, back then we weren't referring to it as agentic yet 2 years ago, but this agentic thing, I can actually store it back in my database. And that is something we talk about as transformation agents. So one of the things that we start to see happening now is that if you query data and you find data, you can actually also give, and that's in our case, the database agent an instruction to fix something in the data. And that is something that I'm extremely excited about, because everything that we've been talking about until now is about better querying. Super important. 80% of the data of the world's data is unstructured. So everything we can do to retrieve it better is welcome. But now we also start to see that we can transform the data that we have retrieved. And that is something that I cannot explain how excited I am about that. And even if I look at the code that people are writing, you see the actual, for example, Python, but then you see like the natural language instructions in it. And the agents just go like, don't worry about it. I'll take care of it. And that's like that's fantastic, man. That's amazing.
Awesome. Now, if anybody wanted to find more information about Weaviate and about your company, where would they go?
Weaviate.io. They can start playing open source. They can sign up for sandboxes. They can reach out to us. They can do whatever they want. We have a lot of educational content as well. So if people want to learn about it, but just start at weaviate.io and then you're good to go from there.
Awesome. Thanks so much, Bob, for sharing your insights today. And thanks everyone for joining us today.